Yesterday, when we first looked at shifting curves, most of those curves involved translations, reflections. Let's have a look at these ones. Constant times function x. Well, that doesn't involve a translation or a reflection. That involves what we call a dilation. It's where the curve gets stretched. So another way of thinking about it, so again, if I grouped it with the y, because I can't get that constant inside the function, so it's actually the range that's going to be affected here. So y over k is equal to function x. If that constant is greater than 1, the curve will become steeper. I suppose if we look at the first way I wrote it, that becomes a bit more obvious, because if we're multiplying the y value by something bigger than 1, well, it's going to go higher up, so the curve becomes steeper. And so if it's in between 0 and 1, the curve will become shallower. So again, we don't worry about negatives, we don't worry about 0, and 1 obviously would be a silly one to worry about as well. But what the effect is, we're going to stretch the curve vertically. So the domain is not going to change, it's the range. It's like we're going to pull it out or push it in depending on what the k is. So the domain should be unchanged, the range will be altered on that one. Now when the constant is inside the function, so it's a constant times x, now it's the domain that's going to change. Interestingly, when k is greater than 1, the curve still gets steeper, and when k is in between the 1 and 0, the curve is shallower. So that hasn't changed. But you'll also notice when I've grouped it with the x, it's k times x, but when I grouped it with the y, it was y divided by k, and so that's why we actually end up with the same feature of curve getting steeper, curve getting shallower. So it's stretched horizontally, so now it's pulling it out or pushing it in. So the domain will change on this one, the range shouldn't change. Always an interesting graph, reciprocal graphs. So 1 divided by the function. So all your x-intercepts of the original curve now become asymptotes, because now you're going to get 0 on the bottom of a fraction, which of course you can't have. And the reverse should happen. If the original graph had vertical asymptotes, they will become x-intercepts, sort of. I'll explain what I mean by sort of later. But if the original y value is greater than 1, turn it upside down, it'll become less than 1, and vice versa. The original one was less than 1, it'll become greater than 1. So knowing where the y value of 1 is on these curves is very important. So on one graph, we're going to draw these 3 different ones. We'll start with a straight line, because we know what these look like, but it'll allow us to illustrate the idea. So if I draw y equals x, there's y equals x. Now if I have y equals a half x, I could think of this as 2 ways actually. Because of the nature of this function, I could say it's a constant times x. That constant is in between 0 and 1, so the curve should become shallower. Or I could move it over with the y and say y divided by a half, but once again the constant is a half, so it becomes shallower. In reality we know there it is, there's the straight line, sure enough it's shallower. So I could again think of it 2 ways. If it is grouped with the y values, because its k is half and I'm making it shallower, I've pushed the red line down. Or if I'm thinking of it as a horizontal one where I've multiplied it by the x, then I've stretched it out. And there's y equals 2x, it becomes a steeper one. Now, we can use that same idea with any shape. Let's have a look what happens with our parabola. It becomes a little bit more obvious. Hey, there it is. Y equals x squared. Now, y equals a half x squared. It's a constant. It's in between 0 and 1. I've multiplied it by the function itself. So this time it's not multiplied by the x. So this should affect the range, not the domain. If I group it with the y, it's y over a half. But it's going to become shallower. So I'm getting this red parabola and pushing it down. I'm making it shallower. So I get the blue parabola. Whereas y equals 2x, I'm making it steeper. So I'm pulling the parabola up, and I get the green parabola. X squared plus y squared on 4 is equal to 1. Let's now apply the idea. The basic curve would be the circle. X squared plus y squared is equal to 1. But how have we changed it? Instead of y squared, I've got y squared on 4, or perhaps a better way of thinking about that is y on 2 all squared. But essentially it's grouped with the y. So it's the range that is changing. Now I said it was y divided by 2. 2 is a number bigger than 1, so it should become a steeper curve. So this means I'm getting my circle and pulling it out vertically, because I'm going to make it steeper. Okay? And by a factor of 2, every y value a double, we get an ellipse. So I've pulled it out, whang, my circle becomes an ellipse. Let's have a look at a reciprocal graph. Y equals 1 on 2 minus x squared. So let's construct it right from the most basic curve I can see there, which is x squared. So let's see how I turn my parabola into y equals 1 on 2 minus x squared. So the first thing I notice is that negative. I'm going to reflect in the x-axis. Boop. There we go. Now, 2 minus x squared. That would be a vertical shift, because it's not grouped with the x. So we're going to shift it up 2 units. There we go. And we're now going to find the reciprocal of this parabola. At the moment we've got y equals 2 minus x squared. Okay. X-intercepts will become asymptotes. So minus the square root of 2 and the square root of 2, I know we have now got vertical asymptotes. Any number that's bigger than 1 will become smaller than 1, and vice versa. So knowing where 1 is important. The other one I've just done there is, well, the y-intercept. If I turn 2 upside down, I'll get a half. All right. What I've done there is I've shaded in the region for y is less than 1. So that horizontal, think of the top of that green rectangle there, is where y equals 1. And what I'm saying is, whenever that parabola is above, it will become below. And whenever it is below, it'll become above. And down there, same thing happens with negative 1. Whenever it's above, it's below. So, what I've essentially shaded here is between this point here and this point here, the parabola is above 1. Therefore, I know the new curve will be somewhere in that green section. It'll be below 1. With the ones underneath, I'm saying, well, hang on. Way out here on the right-hand side, the parabola was below negative 1. So when I turn it upside down, it'll be somewhere in this green section. It'll go above negative 1. Okay. Similar idea. I also know the curve will go in those sections as well. So 1, knowing where the level of 1 is important. And I'm saying whenever the parabola, original parabola is above, it'll go below. Whenever it's below, it'll go above. Basically, it's going upside down. I know other things. I know curves must bend towards asymptotes, so I've got a rough idea what the shape's got to do, and so on. And that red curve then is y equals 1 on 2 minus x squared. So you can see what I was saying. Where the blue curve was above the green section, the red curve is below, and so on and so on. And let's get rid of the construction. Ooh, there it is, the nice red curve. Let's move on to this next one, where we add 2 graphs together. I think we call that superpositioning. It's got some fancy name anyway. So y equals x plus 1 on x. What would that look like? So what I tend to do is, alright, if I'm unsure, I'll draw the 2 basic curves, y equals x and y equals 1 on x. And I'm going to add together every y value. Now I'll pick important ones. So the points of intersection is a logical one to pick, because then I know, oh, well, it's twice that y value. Now, x-intercepts, well in this case, the x-intercept is irrelevant, because it's only got one x-intercept, y equals x has, but that's at a point where the hyperbola doesn't exist. Again, I can't add something that exists with something that doesn't exist. So if it doesn't exist in one, it's not going to exist in the new function. So this is going to have no x-intercepts. But if I did have a curve with an x-intercept, that would be a good one to choose because I'm only adding 0, which means it's going to be on the other curve at the same spot. So I've got a vertical asymptote there at the y-axis. That's going to remain. Point of intersection, that's what I was saying before, because they'll be twice the y value. So I'll plot those. And basically, I just pick as many points as I need to get an idea of the curve. I tend to add the smaller number to the bigger number. So I'll go along here and from 0 to the right, and I'll actually get a ruler and say, oh, okay, that's 1 centimetre above the x-axis. I'll add 1 centimetre to the other curve, and so on. So, plot some points in. There we go. So I've added a whole heap. Things you'll notice though, after a while you'll go, oh yeah, this kind of makes sense. If you look at the right hand side, the hyperbola is getting closer and closer and closer to 0. So I'm adding closer and closer and closer to 0. So logically my new curve is getting closer and closer and closer to the line y equals x. In fact, y equals x becomes an asymptote. That's why we call it an oblique asymptote, an asymptote that's at an angle. So let's draw it in. Whoop. There's my nice red curve. And I'll get rid of the construction. So, nice one. Y equals x plus 1 on x. Oh, that'll do us. 2j. 2j.